Last video for this chapter. Let's talk about the atomic weights from the periodic table. So you might have noticed on the periodic table that some of the weights, actually really all of them, are not right on an integer value. Some of them are really close. Some of them are really, really close to being right on an integer value. And some of them we actually just round to being exactly an integer value. But the vast majority of the mass numbers are some fraction of an AMU. So the chlorine, for example, being 35.45. How do you get fractions of an AMU? Because we said earlier that the mass of a proton and a neutron are essentially exactly one AMU. So how can we get a half of a proton or a neutron? That just doesn't make any sense. How do we get fractions of those things? Well, the answer is that the mass number on the periodic table is not the mass number of a single atom. What the periodic table gives us is actually a weighted average of all the atoms, all the isotopes of an atom. So carbon, for example, has 3 different semi-commonly occurring isotopes. Really, it's just 2, but carbon-14 is around a decent bit, enough for us to measure. But the vast majority of it is carbon-12 and carbon-13. So carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. Carbon-13 makes up about 1% of the total amount of carbon that you would find if you were just to go out into the world and take a random sampling of carbon. You would get about 1% carbon-13. And so what the mass number on the periodic table does is it takes that the relative abundance of the different isotopes into account, and it gives you a weighted average. So what the mass on the periodic table is not saying, if you were to go out and find a single atom of carbon, it would weigh 12.01 AMU. You could never actually find any elements anywhere, any atom of carbon that weighed 12.01 AMU. There's not a single atom in existence of carbon that weighs that amount. Instead, what it's saying is if you were to go out into nature and take a big scoop of carbon, the average mass of one of those carbon atoms would be 12.01. So it's the weighted average. It's taking all of the atoms into account and saying, on average, this is what an atom of carbon weighs. So the way that we calculate this is by taking its percent abundance, or taking the percent abundance of each different isotope, converting that percentage into a decimal, which is just to say that we move the decimal point over 2 spaces, and we multiply those relative abundances by the individual masses of the different isotopes. So for carbon, for example, because 98.93% of carbon is carbon-12, which has a mass of exactly 12 AMU by definition, and because we have 1.07% of carbon-13, which has a mass of 13.0035, we just take those relative abundances. Notice again here, these are the same. We've just taken the decimal point and moved it over 2 places. So we've converted it out of a percentage, essentially. We just multiply those abundances by the mass and add them together, and that gives us the mass number from the periodic table. So the carbon-14 in this case is just so tiny. It's there, and it technically would have an effect on the average mass, but it's so tiny that we can ignore it. So here's a question for us. A fictitious element is composed of isotopes A and B with masses of 61.9887, so essentially 62, and essentially 65 for the second one, respectively. The atomic mass, so the mass that would be put on the periodic table, is 64.5. What can you conclude about the natural abundance of these two isotopes? Is it A, the natural abundance of isotope A must be greater than the natural abundance of isotope B? Option B is just essentially swapping, saying B is more abundant than A. Option C, the natural abundance of both isotopes is about equal. Or D, there we can't tell anything. There's not enough information. So why don't you pause the video for a second and think about that and work out which one of these is correct. Alright, I hope you thought about that for a minute, and hopefully we're able to figure out that the correct answer is B. The natural abundance of isotope B must be greater than the natural abundance of isotope A. Remember, the atomic mass is the weighted average, so the thing that you have more of is going to have a greater effect on the atomic mass. The atomic mass is going to be closer to that isotope, the one that you have more of. And if we compare the masses of the two isotopes to the atomic mass, this is clearly a lot closer to isotope B than it is to isotope A. So it's, we still have a decent bit of isotope A. It's not like carbon-14 where it's such a tiny amount that doesn't even have an effect, but it is definitely a lot less. We have a lot less of it than we do isotope B. Alright, one more example here, and then we'll be done. So, gallium has two naturally occurring isotopes, gallium-69, which has that mass, and a natural abundance of 60.11%, and gallium-71, with a mass of 70.9247, and a natural abundance of 39.89%. Calculate the atomic mass of gallium. So what we're doing here is the same thing we did here. We're just finding the atomic mass by taking the decimal form of the abundance, multiplying it by the individual mass of the isotope, and then adding all the isotopes together. So in this case, we only have two isotopes, just like with the carbon. So we'll do the gallium-69 first. So the mass is 68.9256 AMU. We're going to multiply that by its natural abundance in the decimal form, so not in the percentage. So we're going to move this decimal point over 2 spots. Sorry, my 0 there looked like a 6. 0.6011. And we're going to add to that the other isotope. So the other one is 70.9247 AMU. We're going to multiply that by its decimal form of the percentage, which is 0.3989. And if we do that math, and we round it, what we will get is 69.72 AMU. And that number makes sense because it is it's closer to this mass number than it is to this one, but not by a ton, because there's really not a huge difference. Like I said, we have about 60% of gallium-69, which leaves 40% essentially of gallium-71. So it's not that we have tons of one and just a little bit of the other, but we should be closer to 69 than we are to 71, and we are closer. We're about 0.3 AMU closer. So this number makes sense to me, and it matches what's in the periodic table, so that is always good. All right, I hope that makes sense. If you have any questions, feel free to email, and if not, I will see you the next time we get together. Good luck.